Our speaker tonight previously worked at Intel, working on enterprise-grade distributed storage systems. He's currently the chief engineer at NuoDB. Please welcome Trent Palmer.
Can you hear me?
Yeah.
Okay. So, tonight I come to you as one of the faithful over at NuoDB, and I'm going to talk about distributed databases in general, and specifically about ways of thinking about how you use systems when they're distributed that may have nothing to do with cranking out every last transaction per second, and more about making your lives easier. So this is the obligatory slide where I recap everything everyone knows. So previously on databases, the reason why we're all distributed is because classic sort of single node databases were having trouble keeping up. You could only scale up too much. Manually sharding was driving everyone insane. I know it was making my life miserable. Replication is a pain to set up, so multi-database solutions are equally painful. And so everyone wanted some sort of multi-node distributed database. So here's a reasonable, simplified taxonomy for all the sort of systems out there. So you've got a shared disk kind of system where you have lots of different nodes that are actually processing transactions in memory, but they have a shared durability point. A good example of that is the Oracle RAC, it's a multi-node system. Then the other one, which is just sort of a massive category, is like to use a shared nothing strategy, where you get your parallelism by basically making sure that there is zero intercommunication necessary. And there's loads and loads and loads of systems that take many different approaches to sort of do things like this. But pretty much every NoSQL database is going to kind of live in that space. Then there's synchronous replication, where you have data that moves around and you have very tricky and sophisticated commit protocols involving consensus and clock synchronization to make sure that all of your commits are ordered. The example of this is Google F1. That's the thing that runs on top of Spanner. You're familiar with that? And it's pretty much their baby, and they don't let other people use it. And then there's what we came up with called a durable distributed cache, which is what NuoDB is, which is a set of nodes that are arranged in a peer-to-peer fashion and who can have any piece of data the other ones can have. And it can be shared between one or all, or it could just be on storage somewhere. And it's a much more sort of peer-to-peer, kind of elastic way of looking at the universe. So for people who went the shared disk route, there's some advantages there. First, you get to spread the transactional load across multiple nodes, so more nodes means generally more transactions and generally more memory. And the way it usually works is they've taken sort of what looks like a page in a single database and they've just sort of shared it out amongst them. And one of the nodes is at any given point chosen to be sort of the master who's allowed to do writes. Everyone else is going to be doing reads as some sort of slave. And it's a protocol that has disadvantages, but it's very simple to test and it can be very effective. There are huge minuses, though. One is that it's very vulnerable to outages. If anyone has ever survived an Oracle RAC outage where a single node has gone down, they know how incredibly painful this can be, or like you've had disk failures. They're also outrageously expensive because everything is gated by that one shared storage resource. You have to throw crazy money at it. And which is why Oracle likes it, because they're very good at making sure that you can spend outrageous amounts of money to get that next little incremental performance jump. And so, good there. You can't distribute them around the world, right? Your machines have to be as close to the disk as possible in order to be effective. So it's basically just like having one super big, super expensive database machine in a particular data center somewhere. So good luck having a distributed application. And it's very difficult or sometimes impossible to change the number of nodes. What you get from the factory is what you live with. So this was not an option for many people. Some of these people wanted something more flexible. Some of these people did not have any crazy amounts of money, or they needed failure tolerance. And so the idea was, why not just do the sharding thing automagically? And so that's where this whole category of shared nothing architecture sort of gets their wind in their sails from. So all the initial stuff was just basically about sacrificing as much things about consistency and isolation and stuff as possible to make the automatic sharding stuff work. So on the plus side, it scales pretty trivially across many nodes. Read scaling in particular is super trivial. Writes can scale, although different systems do it different ways, and some systems have serious scaling problems there. It also runs on cheap hardware, which is great for all these cloud kind of situations that everyone is really excited about. And the shards can be distributed widely, so if you want to spread your database across the world, you can, within reason. And you can change the number of nodes with varying ease. Again, it depends upon the system. Some systems make this easy, some systems don't. And a single node failure is survivable. Right? Not always partition. In fact, rarely partition. But single node failures can be survivable. The minuses are basically usually don't have any transactions at all, especially across shards. So there's some that have transactions, but they have to be within a particular data domain, and God help you if you have to do some sort of global database thing. They usually sort of involve crazy locking and are very expensive. Resharding is usually what gets you because the time to reshard scales with the database size. So the databases are constantly trying to load balance. The big ones, unfortunately, they're the ones that are the most expensive to load balance. Another one in terms of operationally and in terms of what the developers are thinking about is that nodes are actually serving shards. They're serving these fragments of the database. They're not actually serving the database as a whole. So caching can be very complicated. Setting that up and making it make sense with your application is non-trivial. And for some systems, when you have failures, you may actually have to copy shards around to restore some sort of redundancy level that you want. And the biggest thing is that basically consistency is a total mind job. Everyone has their own model. Some have no model whatsoever. You have lots of things where you have to solve it with something. Polling, where you have weird situations like these doomstones that keep coming back. And so these problems are well known, and that's why people are sort of still looking for better solutions to these problems. So many people want transactions because transactions are very useful. Basically, if you want to update many discrete pieces of data in an atomic way, they're really handy, and sometimes that's just necessary. Sometimes your application has been constructed in such a way that one extra new feature requires an atomic multi-row update, and some systems really can't do that. And so you either have to implement all this transactional concurrency and consistency control yourself, and the chances of doing that correctly the first time out is very low. So it tends to put a lot of pressure on the application developer to deal with this. And so forcing every application to re-implement the same sort of pieces of core database technology is definitely suboptimal. So we want distributed databases for all of the reasons in the first slide, and we want failure tolerant stuff because having non-failure tolerant distributed databases is insane. But we also want transactions because we want consistency. So the synchronous replication system, Spanner, that actually does bring back true consistency. It is globally distributed, and it uses this sophisticated version of fast Paxos combined with atomic clocks to make sure that you have a global linear order of transactions. And it does support transactional semantics. They're not necessarily the kinds of semantics you would expect from a normal database because it's not serializability, it's linearizability. But hopefully in most cases they're going to be the same. Data placement is dynamic-ish. Different nodes can serve different pieces of the database, and it is specified by the application, but the application has to tell it where to cache things explicitly ahead of time. And it actually supports schema, so you can actually have type checking and you can enforce certain data constraints. The schema is also where you put all of your caching information. So one of the big minuses, from my point of view, and from any developer's point of view, should be that there's a huge amount of application level tuning that has to go on. It's basically a very bare bones system, and the application is responsible for telling the database all of the locality rules and all this other stuff. And so I know from my personal experience, after having written a piece of functionality for a large complicated application, my ability to understand what its locality behavior would be and what would be best to cache is probably very low. And so the chances that I would guess this is very low. So you need to have great benchmarks, and you need to be able to sort of tune this stuff a lot before you deploy it. Another big disadvantage is it's very clock dependent. You need atomic clocks with fancy GPS receivers, and you need really nice high performance WAN connections between these things with very little jitter in order to make sure that your distributed transactions do not suffer. And they do distributed block management for the transactions, which is why LAN jitter causes a huge problem. The other thing, from my point of view, is that the way you specify locality is by the way you specify primary keys. So it's impossible for you to cache in a way that doesn't involve the primary key. You can also only have one primary key. So conflating this notion of being able to uniquely identify rows and that sort of relational characteristics with where you actually want to store this stuff and what the caching behavior is for your application, particularly if that behavior may change over time, is a big disadvantage. So if you don't have 5 atomic clocks, the infrastructure requirements here are a challenge, and so that's why no one's using this with Google. The caching locality must be hand-tuned, which is very easy to get wrong. And the other thing is performance just becomes a responsibility of the application. So the question is what if some crucial component of the underlying infrastructure is changed for some reason that you can't control, and you're just, some company has written an application that runs on this. And the way they change that suddenly has all these performance implications, and you have to retune your entire application, which can take weeks, months, and meanwhile it's slow, and there's nothing you can do about it. Whereas in a normal traditional database, you tell the database what data you want, and it's responsible for making it fast. So in a distributed dynamic cache, which NuoDB is an example, instead of thinking about it as distributing pages from a database, or instead of thinking about it as distributing shards of a massive database, just think of it as a distributed transactional object system. The database is composed of objects. Those objects can be modified in a transactional fashion, and they can be distributed across all the nodes. So they're all peers of one another. When you make a local change on a peer, that becomes a mutation in memory, and then those just become well-ordered messages that flow out to all the other peers who happen to have a copy of this particular object in memory. And so you have two kinds of nodes. You have these transaction processing nodes that accept client connections and then operate on these objects. And so a transaction node is going to be a cache of objects whose contents can change over time, because it's a cache, and a query compiler and execution engine to actually take the strings that the client is handing you and turn them into actual data. And there's an additional kind of node, a storage node, because you have to decouple transaction processing from storage. So the storage nodes are these separate nodes, and their whole job is to basically just receive all these changes in the form of messages, and then just make it durable somehow, right? Just save it all out so that when a particular transaction node's cache is full and it needs to evict objects, it can always, in the worst case, go back to the storage node to fetch a copy of what it needs. So since it's peer-to-peer, nodes come, nodes go. People have to be able to move data around. Caching is done by the system for you. So it's a very different and flexible architecture from these other architectures. There's not a lot of upfront work. You don't have to reason about how your data model has to be chopped into pieces.
How do you guarantee that you're updating the right data and not scale data? How do you ensure that there aren't conflicts on that message you talked about?
Okay, I will give you a one-word answer now, and then we can discuss it after the talk during questions. The one-word answer is actually an acronym, and the acronym is NVCC. So using versions, we can handle this sort of stuff. And the specifics of it are at home, but it's version. So the use case that everyone brings up is performance scaling, as it was the first most important one. So in the shared disk approach, you spread the load amongst a few expensive machines. With a shared nothing approach, you throw lots of cheap machines at your task, and then you make the application stitch together any results that may straddle shards, or whatever you want to call them, but they're shards. And basically, you have to re-implement some consistency model if you're doing anything that looks like a join or an update. With synchronous replication, you're also spreading load amongst shards, but the system is managing it for you, and you trust that the super fast network is going to keep all the synchronous commits cheap. So if you're doing reads, there's no longs. If you're doing writes, then it should be reasonably cheap as long as your network and atomic clocks are in sync. With a durable distributed cache, if what you have isn't fast enough, you can just keep adding new transactional nodes to spread load amongst it. And as their cache warms up, they go from being sort of slow to fast, and they can start serving whatever particular queries happen to be local to that node. So different nodes will have different cache contents, just automatically sort of inferred from the behavior of the application. But everyone talks only about TPS. All they're concerned about is just performance, and this particular kind of performance, because transactions per second isn't the only kind of performance concern that people have. It is very important, but it's also not the whole story. You can have a super fast database, but if your application developers can't develop to it and your operations people can't run it, it's actually useless. So other concerns, latency. Latency is a kind of performance concern that people usually don't bring up. So if you're spreading your data around the world, you may not be running a bajillion transactions per second, but you want your response time to be in the sub 100 millisecond range, right? That can be very challenging. Development effort. If you can roll your application out 6 months before the other guy, that's a huge win. Operational effort. If you don't need to hire an army of people to run your database, it's also a huge win. And so all these things are going to be functions of the underlying architecture as well. And the main focus of this talk is to go through use cases where the architectures show their weaknesses and strengths. So the first use case is latency. This is an actual customer use case where they had this black box VoIP application that needs a database to do customer stuff, basically. And they couldn't or weren't willing to modify the application. And it issued several queries and then did some logging. And their problem was that the time to initiate a call was critical. So if it was a few hundred milliseconds, people wouldn't notice it. But if it took a couple seconds to start a call, then people would quit. They would leave your service. And so they were losing customers because of this. So they started off, and everything was running in the Virginia data center for Amazon. And then they were able to spread to the West Coast, and it was still kind of okay, but it was still that one database in Virginia. Then they got some Far East customers, and they're running in Singapore, and suddenly they were having huge problems because call completion times were over a second. And the VoIP app could be deployed globally. You could run that in every single data center, but they needed a single database somewhere. So the classic solution to this problem, which has been around a while, is you use something like NetRSG. You cache with the Jesus episode. So this is great if your database never changes. Otherwise, your app is going to have to solve the cache invalidation problem. And if logs had ink on them, there would have been a lot of it spilled on all of these problems where people forgot about these horrible edge cases. And the cache invalidation problem is like the consistency problem. These are all things that have been solved, and the idea was to solve them in the database once and get it right and get it fast, so that applications wouldn't have to do that. But if you're caching, all of a sudden the application now has to do that. And if you have a shared disk solution like Oracle RAC, you can't distribute that database, so you still have to use memcached. So all of those advantages go away. And you can't use many of these NoSQL systems for billing information because they're inconsistent. And what people end up doing is hacking together some hybrid system where they bounce a significant fraction of their queries off of some NoSQL thing, and then there's some reconciliation that happens later on against the main database. So that requires a lot of application re-architecting, because that's not how you would sort of initially envisage architecting your application. So if you have the synchronous replication solution, the idea there is, why can't you just run a database node in the same region, and then you just read from more local nodes? So as long as your application knows what needs to be cached, you can start spinning up nodes in the region to be closer to the VoIP server. With a distributed durable cache, you can start asking questions like, why not just run a node on the same machine? Since the number of queries is low and the database is actually not that large, you could actually have your latency, the amount of time it takes for the VoIP app to do its query, drop down to microseconds. It's running on the same node, because local socket is way faster than the network. And this is really trivial with things like NuoDB, because you can just start peers anywhere. So another use case that people are starting to talk about are the so-called hybrid workloads. So basically this is online transaction processing and analytics against the same data. So everyone wants to do analytics, and they want them to be as real-time as possible. The problem with this is that analytic performance characteristics are perverse for online transactional processing. So a lot of analytical queries are going to want to read through everything. So you actually want to do evictions that look more like MRD. Whereas OLTP stuff are kind of randomly probing the database, and so you wanted to have a policy that looks more like LRDB, so they're obviously going to fight. And it's not surprising you run it against a normal database, and if you have a big enough data set that they have to start picking things out of their memory cache, they start to have really bad performance problems. And that's, all that together is known as cache pollution. So the reason why people want this is because consistency makes a developer's life easier. So everything becomes relative to the same snapshot, so it's easier to reason about what your transactions are going to be, but it's also easier to reason about what your analytics are going to be, because everything is at least consistent within that snapshot. The solution that a lot of people have been doing is shunting data to some sort of separate analytical system, but that has problems as well. It doubles costs, because now you have two systems you have to maintain rather than one. You have two programming models, two applications, and it's not real time. And so what everyone wants is some unified data store for both workloads. So if you have a read-only analytical workload, classic databases and shared disks have a problem with this because cache pollution is just going to kill them. With shared nothing, you can add more slaves or nodes basically dedicated to reading whatever the system wants to call them, and make sure that all your analytical workload runs off of them to handle all the read load. And the big problem you may have to deal with is manually joining stuff. You may have some sort of giant software library that helps you do that. For F1 and other these synchronous replicated databases, of which the only example I know is F1, they have a bunch of read-only optimizations so that there's no locking and no messaging that has to happen. But what if you have an analytic workload that is read mostly, where you do lots of reads but occasional writes? Maybe you're checkpointing or something like that. Shared nothing is the same. You may have consistency issues or join issues the application has to solve. For F1, what it does is it buffers all the writes until it commits. And so what you end up maybe having to do is take a big transaction that makes sense logically, and then manually divide it into lots of smaller transactions just so that you don't have to worry about these writes just piling up on the local node and then taking 10 seconds to trickle through the whole system. So the question is, can we support different caching needs automatically in the same database? So with NuoDB and other distributed caches, you would just have different transaction nodes for OLTP analytics. You spin up new nodes, and you would say queries that come in and say I'm an analytic query, send them there. Queries that come in and say I'm an OLTP query, send it there. And since they're different processes, right, then you have performance isolation, even on the same node. You can run them on different nodes. They're going to have their own caches. There can be no cache pollution. So even if the OLTP clients are doing completely different things, they're all going to have their own machines. And so they can't actually fight with each other or the analytic workloads. Okay. And if you have multi-version concurrency control, you can actually have snapshot consistency without blocking any writes. So the writes will only block writers if they happen to be applied to the exact same row version. Otherwise, you'll always be able to read an older version of the database. And so you can have long-running analytical queries that are not going to hold up any active transactions because all the OLTP writes and updates are basically going to be happening far above where the analytic workload is going to be reading. And since analytics, even read mostly ones aren't write contentious, you don't have a performance problem. Another use case people don't talk about, it's not performance per se, but it is very important, is backup. So databases contain valuable data. People want to be able to handle disaster recovery. So you basically, ideally, you want a restorable snapshot. You just want something that you can take out of the box and then start up a backup database on it, or you want some sort of hot standby that you can flip over to. Another reason why people want to do backup or a snapshot of the database is because developers want to have a development database, and nothing beats real-world data. And the major solution still is some form of bizarre replication. Replication sucks. It's very, very hard to set up. And it tends to break all of the consistency models because the minute it leaves the one database machine, it's whatever. And then you have to deal with any problems on the other side. So if you have a shared disk database, you still have to do replication like you always did. With shared nothing, it's kind of all over the map. Some systems have some kind of replication scheme. Others, there's some sort of manual migration where you actually have to have the application make sure that it's sending updates to both places. Consistency is always going to be a concern because if you don't have a consistency model or you have one that can't handle concurrent updates, how are you going to make sure you capture them in the new copy of the database? And that is basically a per system thing. And that doesn't help because then developers won't, they're really good at dealing with, some sort of issue in like couch or whatever. They're not going to be able to deal with it in standard because they're very different systems in the raw mechanics of it. With a durable distributed cache, since peers are constantly copying data back and forth anyways, you just spin up a new storage node. So this is actually what our customers do. When they want to back up the database, they just, they spin up an instance if they're on Amazon or something that actually is targeted at storage where they want to keep this copy. They spin up a storage node. He's a peer. He finds all of his friends. He realizes he doesn't have the information he needs, and he starts fetching it from them. And then when he's got the full copy, so we call this process syncing. When it's done syncing, you can then just shut it down, and then you have a consistent snapshot of the database at that point in time. So you've just made a backup, and it required 2 commands, and some waiting if it's a very large database. And so, peer-to-peer systems move data all the time, which is why this is sort of just a side effect of the architecture that you can do this. And while it's running, you actually have an extra bit of redundancy going on. And you can scale this out consistently. And since most of the load is being put on the new storage node, you're not actually going to have performance problems with the other things, which is another important thing. And what this really means is that you don't have any downtime. So you can back up on them. Just spin up this guy, wait for him to finish, and just spin it down. And the other nice thing is that they can sync from all other nodes. So it doesn't have to go to another storage node somewhere. If someone nearby with lower latency and lower load has a copy of the same distributed object, will just fetch it from them. And all of the mechanisms you have to have in a distributed object system to make sure that updates get where they need to go are going to be in play here so that these things can be updated concurrently and they're not going to be locked. And the storage node is going to get a copy of this object, and it's going to also receive all the messages telling it what changed so that it can write them all out to some sort of permanent storage. So an extension of the backup use case is storage migration, which is like the big problem for most of your DB operators out there. So you need to move from some old, slow storage or small to new, wonderful storage. And the thing that makes it really awful is that online migration is basically solving the backup problem and then doing a controlled failover. And you have to make sure that you get all the ongoing transactions while this is happening, which is not always trivial in systems. And you also need to be able to deal with the fact that you might be putting a lot of load on the system and you might actually get node failures while you're in the middle of this. So if you have a shared disk solution, it's basically like having a single node database as well. The standard recipe is replication and prayer. And then, basically, if you get everything over there, then usually what follows is a massive amount of testing. Massive amounts of testing. And then you fail over the new die, and then you actually keep the old one up and around for quite a long period of time until you're absolutely completely positive that you've got everything over. It's very expensive, very difficult, and many people have gotten gray hairs doing this. With these shared nothing solutions, again, that's very dependent upon the system. So some of them you can do a kind of replication, but the application has to move the changes over for you. Or sometimes they'll let you actually increase the size of the database, and then you'll basically increase it onto all the new storage, and then you'll shrink it back down. The complicating factor here is that many of them require you to increase it by a large amount. So you have to double the size of the database or something like that. And that can be very expensive, especially if it takes the big database, it's going to take a long time. Or sometimes you can do incremental replacement, where one at a time you sort of upgrade these things. But there's no consistency there. With a distributed durable cache, you can add new peers on the new storage, and they just start up like normal storage. And it doesn't impact the way the application is working, and so the ops people are free to decide how they want to do it. If it makes sense for them to do it all at once, or if they want to do it in a much more incremental fashion, where they spin up a new guy, they shut down an old guy. Developers don't have to get involved at all. There are no spurious failures involved by this, because when you shut down the old guys, it's not like you're just killing them. And there's no interruptions while this is going on, because these are just new peers and the storage, and they're not going to be accepting new transactions. And the other nice thing is that as these new peers start to get objects, they can start serving them immediately, even though they don't have its whole database yet. And so it's basically just a scale out followed by a scale back. So if you can handle both scaling out and scaling back on storage, then you could do migration. So basically, architecture really matters. So if you focus only on just raw TPS, then you're kind of missing a bigger picture. So you may sacrifice things you want later. And so what people have sort of noticed is that you want consistency because it makes applications understandable, which means it makes them much easier to implement, which means it saves you a lot of development time. You want transactions because it makes it easier to write applications that have to update lots of things. You want elasticity if you're an ops person because it makes administration simpler. If it's cheap to spin up new nodes, then you don't worry about losing old nodes quite as much. And you can solve a lot of these problems of backup and migration in a much more trivial way if you can just add new nodes with impunity. And caching makes applications faster. And if the application doesn't have to explicitly specify what the caching rules are, then it makes the applications easier to develop. So if you go with something like shared disk, what you're gaining is faster inter-node communication there, which is a plus, but you lose the ability to be multi-data center, and you're forced to do replication again. You also lose failure tolerance. If you go with something that's shared nothing, you gain the ease of loading many cheap nodes, but you lose elasticity with large data. So the database gets bigger and bigger and bigger. It becomes harder to sort of be flexible. And in many cases, you lose consistency or strong consistency, and you lose the ability to do sort of arbitrary transactions. If you go with some synchronous replication solution, you regain maximum transactionality, but the program model is subtly different, so you have to get used to that. And you lose the automatic caching, so the application level tuning becomes very important, so you end up spending a lot of your time doing that rather than developing the application logic. And you also lose the convenience of cheap nodes and cheap networks, so you can't just have some hack to get a developer system and other stuff. You have to be running on basically production hardware all the time. With a durable distributed cache, you can regain transactions and consistency. You regain automatic caching, and because it's elastic, you gain operational simplicity and flexibility. But you do lose the tight coupling between application and data lab, which is something you could always get with the old database. It may matter to some people, but the system, because of the needs of flexibility, you introduce indirection there. And you also don't have a tight coupling of in-memory and on-disk format, which is another feature of old databases. That again may matter to some people, but not. So it depends on what you are who you are as to whether or not you consider that to be a bug or a feature. I think it's a feature, but yeah. So thanks. Now I'm going to try and do a quick demo, although the screen real estate here is way smaller than I was expecting. But I have 4 VMs running here simulating basically 2 regions separated with high latency. So you have these 2 machines that are separated by about 10 milliseconds, and then these 2 machines that are separated by about 10 milliseconds. But both halves are separated by about 300 and something milliseconds. So we start up our database here, and then we can run our cheesy little latency detecting application. Okay. So you can see here it's doing this little latency thing, and now we run it on the node that has a 300 plus millisecond hop over to the server, and it's taking a lot longer to do this. So this is basically the situation with the latency problem we ran into with an actual customer. So at this point, you know, if you were actually dealing with, and this was your application, someone said this is unacceptable, there'd be a huge debate. There'd be a room full of loudmouths like myself, and some people would say like, oh, we need to cache. I didn't have cache in my last job. And they'd be screaming at you and everything like that. And other people would say like, no, you're stupid. We need to hack on the application and make sure that it does it all in one transaction rather than 3 or 4, or that it batches it, and we need stored procedures or whatever. And those arguments could go on for days. Now, if you're lucky, there's a young person, someone who just hired, who has no idea how to do things the right way. And they'll just be thinking, well, maybe I could just start up a little management client here. Okay, and so I can see that I'm running, this SM here is a storage manager, this is a transaction engine, so I'm running them all over on this is the left coast, the other side is the correct coast. And so this person says, well, why don't we just start the transaction processing node on something over on the correct coast. We have a machine, it's called the server. Maybe that'll do it. Okay. All right, so we see that it's running. Okay. Nothing yet. But what's going on right now is this guy over here on the correct coast, this client, he's going to start trying to connect to the server that's near him, and then that guy's going to have to pull in information over here. So it's going to be this initial warm-up period while it brings over all of these objects to satisfy the first few queries. And as you can see, now all of a sudden you're talking about 100 and 150 milliseconds up there. And you didn't have to change a line of code in the application. You would just start up a new server over on the data center. And then, so the young person is screaming, you know, look, I solved the problem, and all the old people like myself don't believe him at all. And they yell and think he's insane, or it's just some sort of artifact or something. And then what you can do is you can actually say, well, why don't I just run it on the same machine that the client's running on, because it's a small database. It's only, you know, 100 megabytes or something. And we don't need a lot of memory. So we started it up. And now this guy is talking to the local. And as you can see, well, maybe, so ideally there would have been enough space to have all these next to each other, but this guy, he hasn't been impacted by this at all. He's just trundling along, he's doing fine. So all the left coast calls are completing nicely. And then over here, he's populating the cache on the local machine. And there you can see the very top bucket of the histogram is actually starting to fill up. And so this is over the whole history of things. So now all of a sudden you've got the client running on the correct coast is now all of a sudden faster than your client on the left coast. And all you had to do was just start up a couple of nodes. You didn't have to do anything in your application, and it just reacted. Okay, so thank you. That was the talk.
guys have already given the track a great round of applause. Thank you. I do want to remind you we are giving away a Raspberry Pi with a awesome development kit. Someone is going to win that here. In order to enter that, you do have to have your name in this bucket, either via a business card or by filling out one of these papers that are already left. So you need a business card. Just pass this around one time. That's okay. So everyone can kind of just throw their card in there, and then we'll shortly give that away. And let's take the first question. Hands?
Like full SQL compliance, including those parts of SQL that are going to be old and fuzzy and all this other stuff. And yeah, and so we have customers that are actually going to be using it to replace more well-known databases in the core of their system. Again, for a lot of these operational reasons, actually. Some for performance, but mostly because of operational flexibility, because we're moving from a classical system where you sell a big deployment to a customer where they have some big central server and a bunch of clients, and now all of a sudden they want to do everything as a service, or they want to do it on a cloud-like stuff or whatever, and suddenly have a flexible database that's SQL is transactionally consistent. It matters a whole lot. Yeah, it's secure by default. Everything is encrypted. There's no way to turn it off. You have to specify users ahead of time. It is secure by default.
Next question?
Any update question?
You said MVCC
Yeah.
solves your problems with multiple updates in different data centers for the same documents or records or rows or
yeah, it's not
key value store. I
don't
don't know what you store.
Yeah, so we are row-based, right? So we're a relational database. We have rows. So every row is basically versioned. So when you do an update, it installs a new version on top, right? And so with multi-version concurrency control, as you're going through, basically what you end up doing is you end up grabbing all the rows that could potentially satisfy your query, and then you filter them out based on ones that you can't see because of transactional visibility rules. So if you're doing an update, you're going through and you're finding a row that matches your predicate, you're updating, you're installing a new version on top. Only if you have two transactions updating the exact same row version at the exact same moment, does there have to be any coordination. So if that happens, right, so everything is very optimistic. So I'm running a transaction, I've got a global client, he's issuing some sort of update. I'm fetching the set of objects that's going to be describing the range of many thousands of rows that I'm going to be going through. And if I look at it and I say, you know, hey, there's no one currently updating that, it's totally safe for me to do that, I'm going to install a new version, and I'm going to give it this version number and assume that it's cool, and then I'm going to move on to the next row. Meanwhile, I'm going to send a message off saying, this is what I'm doing. Okay? So for any given object, at any given moment, there's going to be someone who can act as a tiebreaker. You've got races for these sorts of things. So if you are the tiebreaker, then you can kind of declare yourself the winner at that moment. If you're not the tiebreaker, then you wait for the response back before you can declare this update to be finished. Right? And this is an interesting thing where we could be faster if the semantics of SQL were a little different. So SQL began life as this weird interactive shell, so it has this odd bit of semantics where the return of updates and inserts has to be precise. So when you get that number back, it tells you I updated exactly this many rows and they're currently durable. I mean, the funny thing is if you commit and, you know, who knows what could happen between when that transaction ended and the next one began or whatever, but I don't know how useful that information generally is, but you have to wait until every single update that you're doing is completely confirmed before you can actually return any information back to the client. So even though you may have a transaction that has multiple statements, you actually have to have these sort of synchronization points after each statement. And so basically we can update everything optimistically, and then when we reach one of these synchronization points, we have to sort of pause and wait for sort of information to come back. Most of the time it's just, you know, everything is good. And so we get to overlap multi-row updates with each other, so the cost tends to come out the wash.
Right, but in the scope of the transaction, you have to wait until it actually finishes, right?
Wait until what actually finishes?
The transaction. For the client to get a receipt of the transaction,
Mm-hmm.
you have to wait till it's done. If the transaction engines are across the country, does that mean each transaction and each engine that might have overlap needs to wait?
No, so that's where the locality is going to help you, right? So if you have an application that really does have to update the exact same row at like 10 points on the surface of the Earth at the same time, then you're going to have to communicate, right? But if you have any locality in your application at all, the objects specifying the rows that this particular client is interested in are going to be pretty much mostly disjoint from the set of rows that are going to be, that this other client on this other side of the world is going to be interested in, and only if they actually have a collision at the exact same row are they going to have to deal with it. The objects themselves are very fine-grained, so the tiebreakers tend to be in the same data center as the clients.
Sure, but you said in one of your examples that your database is great because you don't have to change your application.
Yeah.
So if your application is poorly architected, let's say poorly architected in the term of every time you have to update a row, it's the same row across all transactions.
Yeah, no, that's true. I didn't say you never had to update your application. I said if you have an application that works well against the database,
Sure,
you do lots of clients, and it works well against the database, chances are you're not going to have to tear it all apart and rewrite it from scratch just to get it to run against 2 machines running a database, or 2 machines in 2 different data centers running a database. So yeah, if you write a badly architected application where at the beginning of every transaction everybody hammers on the same row, at the end of the transaction everybody hammers on that exact same row again, you are forcing serialization of every transaction in your system across the world, and that is not going to be fast.
Next question, please. Yes, right there.
How do you handle your distribution of rows against your available nodes in the cluster?
Well, it's a distributed object system, so a transaction engine is basically a giant cache of objects, so a pile of memory, and then something that can interpret the SQL and compile it down to an execution plan. So if I need an atom to satisfy, we call our distributed objects atoms, so forgive me if I accidentally say atom instead of object. If you need an object to satisfy a query, you go and fetch it from a peer if you don't have it, right? And then you execute against it locally, and then as your cache fills up, you start doing capacity eviction to free up space. So it's application driven, basically.
Next question. Hands, anybody? You're itching for another one, so go for it.
I had a few questions during the talk, so I thought I'd ask them again. You mentioned earlier about cache pollution.
Yeah.
And you said that multiple processes didn't have that problem, but you also mentioned running on the same host.
So multiple processes won't pollute each other's memory, right? Because the operating system is making sure that they have completely different address spaces. But if you're competing for the same physical memory, you have the same problem, right? So obviously, if you want to run 20 million databases, running them all on the same machine, if you don't have enough memory, is a bad idea. But because they're already isolated from one another, right? They're 2 processes running on the same machine is, from the point of view of each of these individual processes, no different than 2 processes running on 2 different machines. So if you have enough memory to spread amongst the multiple processes, you're free to do that. And we have, we do these high density sorts of things where we actually do pack thousands upon thousands of running processes, because that's how we do multi-tenancy for each individual process. And as long as they're only using, dozens of megabytes, you can actually squeeze a hell of a lot of them into a single machine, and they don't actually fight much. But yeah, if you have this big thing where you're doing like massive amounts of memory, churn and everything like that, you don't want to have these 2 competing for each other in the same physical memory, especially if the physical memory is much, much smaller than the logical addressable memory. And so then, yeah, it makes sense to run on multiple machines. But you actually have that flexibility. So if I'm a developer, I can just run 7 processes on my local laptop and develop against it as if it were the other thing. Whereas operationally, I'm going to be running on real machines with serious memory.
So how do you know when they store the same copy of the same object, when they compete by having redundancy, for example? Is there a deployment scenario that you suggest that guarantees that they don't all cache the same thing?
No. So if you're asking sort of how do we stop, like if you're running multiple processes on the same machine and you're worried about sort of double or multi caching or whatever, we don't. If it's needed for that particular node, it will fetch it, right? So if you're running on different nodes, different machines, then that's not a problem. If we're all running on the same machine, there's no sort of negotiation mechanism to say like, oh, you all have object 17 in memory, so we'll just keep one particular copy there.
Okay, that's all. Oh, okay, we get one more.
What's the limit to the amount of processes or capacity that this database can do on any particular node?
On any particular machine? Well, in practice, what we run into is that most Linux deployments have view limits of file descriptors or processes or memory set low that, usually after a few hundred, you start running into those, so you have to pump it up. But generally, like, if you have enough resources to run many of these things on one node, you can run as many as you want until the machine, keels over. Basically, they're each separate processes, right? So every operating system is going to have a number of processes limit, and they're each going to be operating on data, so you want that data to be in memory, and so your physical data is also, your physical memory side is also going to establish limits for that. But that's going to be dependent on the actual machine, because they're just processes.
Okay, that's all the time we have for questions. Trek will be here for one-on-one questions afterwards. We are about to give away this Raspberry Pi, but before we do, I'd like to give a great big round of applause. Thank you, Trek.
And if anyone wants a copy of the slides, just come see me, and I can get your email, you can get my card, and I'll send it to you.
Okay, can I ask you to mix that up? Just to mix that up. Would you like NuoDB then? Okay, now look in the other direction, reach and pull out the card.
Yes.
Okay.